Okay, so second part of this one, yeah, let's look at this. So if this is the function and the asymptote is x plus 1, right?
Yeah.
Oh, it's frozen. So the second part wants to know, where does the function intersect its asymptote? Well, how do you find out where functions intersect, where graphs intersect? What do you do? So, okay, solve. You're right. What are you solving? What do you solve? You set them equal, right? Okay, does that make sense? Now, why do you do that? Well, because we want to know, this is the asymptote, so we should probably call that not f of x. Let's call that like g of x. How about? So here, this is calculating the outputs, the y values for the function. That's what this algorithm is doing, right? We input x values and we figure out what the y values are based on this algorithm. We input x values and calculate the y values based on this algorithm. Where graphs intersect, the x and y coordinates have to be identical, don't they? Right? So really, when we set the equations equal to each other, all we're doing is we're asking the math gods, where does this y value equal that y value, right? So so this one's going to be red. And this one's going to be blue, right? If I set the red y values equal to the blue y values, and when I ask the question where to the math gods, what's implied is when I say where, what I really mean is for what x values, right? We want to know for what value of the input variable x. So when I solve this thing, the resulting x values are going to be the places where this is true, where the red function equals the blue function. Okay, this looks horribly difficult, but it's not very bad. I mean, I would just cross multiply here, wouldn't I? If I'm going to solve this equation, it's a proportion. I've got this fraction equal to that fraction, so we just cross multiply. And we end up with x to the fourth times x plus 1. Well, if we do that cross product, what do we get? If I distribute the x all the way through, I'm going to get x to the fourth plus x, right? If I distribute the 1 all the way through, I'm x to the fifth, sorry.
Okay.
If I distribute the 1 all the way through, I get an x to the fourth. That should be a 1. That should have been an x, right? Yeah. Should get that. Right?
Yeah.
If I do this cross product, well, I just get that. Okay, well, that's pretty convenient because almost everything cancels, doesn't it? Right? Look, the x to the fifth subtract away, the x to the fourth subtract away, the 1 subtracts away, and all I end up with is x equals x squared, which is a pretty easy equation to solve. Right? Subtract x from both sides, you get x squared minus x equals 0. You get to solve that. That's no big deal. I get 2x values pretty easily, right? Okay? Make sense? All right. Yeah. Okay, it's a good question. Oh, kind of wrong. Did I? Oh, no, we're good. Okay, this is, yeah, here we are. Okay, so we were talking about formal definitions of limit history. Let's wrap that up. So, just to kind of refresh our memories on this a little bit. So we say, the limit of f of x as x approaches c equals L. What we really mean by that is, remember, if f of x becomes arbitrarily close to L as x approaches c from either side, then this makes sense as a limit. And that word arbitrary is really key here, right? We can get as close as we need to the answer L. Let's go ahead and flip all the Chromebooks all the way close. We can get as close as we need to L by simply getting closer to C. right? Shrinking our neighborhood down of values surrounding C. Okay, doesn't work here, right? Here it fails because I can't, by shrinking the neighborhood, I can't get arbitrarily close to L from the right. As I approach from the right, I'm still going to be really far away from L, even if I get super close to C from the right. So it fails. And that's why that limit fails to exist, because this relationship does not exist there. This is the essential relationship in order for a limit to make sense. Failed there, right? Because once again, getting arbitrarily close to C doesn't push me towards a single value of L. There is no single value I move towards. So once again, that's a limit that fails to exist, as we mentioned much earlier in the year. And same thing here, right? This thing's going to oscillate through large amplitude regardless of how close I get to C. Okay? All right, so here's where we kind of left off then. Let's look at some examples. And I think I'm going to skip through that one. I think we'll just go to maybe this guy. So the function f is, the graph of the function f is given. For each value of epsilon. Now is epsilon, is that the y? Is that a y issue or an x issue? It's y, isn't it? If we go back to our picture. Epsilon is like our target accuracy, right? How close do we need to get to the actual answer of our limit? The delta is the width of the neighborhood. Well, the half the width of the neighborhood. That has to do with the x value. So for each value of epsilon, find all the values, the positive values of delta, such that the absolute value of f of x minus 6 is less than epsilon whenever the absolute value of x minus 2 is greater than 0 and less than delta. In other words, what's the limit that we're approaching in this case? What x value are we approaching? 2. There it is right there, right? Okay, because we're looking at the neighborhood of values that define delta is the distance between x and 2, right? That's the value we're moving towards from the left and the right, okay? So we want to write this as a limit that we're trying to show exists. Or I guess we assume it exists here. Oh, it says it right there, doesn't it? The limit of f of x as x approaches 2 is equal to 6. That makes sense. Because look here, this is saying the distance between f of x and 6 has to be less than our target value. Okay? Make sense?
Yeah.
Okay? So what if epsilon is 2? Well, let's look at our graph down here. If epsilon is 2, here's the value we're approaching, right? There's 6. Okay, so if epsilon is 2, I want to be somewhere, that's the wrong thing. There. So I want to be, that's the maximum y value I can tolerate, 6 plus 2, and there's the minimum y value I can tolerate. Agreed?
Yeah.
Okay. So then what's the smallest, say it again, what's the largest value of delta that would work?
6. Well,
Of delta.
Delta.
And delta is the distance to the
3.
left or the right from
4.
2.
It's from
Okay, yeah, look at this here. So here's where we want to be, right? If I move to the left, I can only go 1 away before I'm already outside of my target accuracy.
I thought we were looking at the greatest. I'm sorry.
No, we want the
The large.
we want the greatest tolerable value, right? Like you might be thinking, what people would tend to say here, like just say somebody throws out the number 4, because look, that's 1, 2, 3, 4, right? To the right, I could be up to 4 units away from 2 and still be within my target accuracy for y. Agreed?
Yeah.
But this is a two-sided limit, so we can't necessarily guarantee that we're approaching from the right in this case. So any value we throw out here has to work from both the left and the right.
Okay.
The left is a little more critical because the left is a steeper function, right? So from the left, I can only go one away, and so the answer is one, right? The width of my neighborhood, to guarantee that I'm going to be within my epsilon, I'd have to say that delta has to be less than one, right? Because there's a chance I'm going to be approaching from the left. Make sense?
Yeah.
Okay, that's all this is. So it's really, there's no calculus to do here. It's just a matter of understanding what we're talking about. So this is going to give us delta equals 1, okay? Because that's the maximum extent of my neighborhood. What if epsilon is 1? That's just going to shrink these, right? That's just going to move these up and down. So it tightens up the window. Be a half, then, wouldn't it? Right? Because I can only be I'd have to be within a half, because if I'm approaching from the left, I gotta be only less than a half away from 2 in order to be within my epsilon. Okay? So, for any epsilon, can you make a conjecture about the corresponding value of delta? When epsilon was 2, delta was 1. When epsilon was 1, delta was 1/2. So delta, in terms of epsilon, what is delta?
It's one.
1/2 epsilon, or epsilon over 2? Agreed? Okay. How come? Can you relate that to the graph? Where's that number 2 come out of the graph?
It comes from-
It is?
Well, it's centered around 2.
Okay, yeah, so there's a 2, but that's not the 2 I'm looking for. I mean, I could have dragged this whole thing over to the right, and it could have been centered on 12, and it would have been the same answer, though, wouldn't it? Nothing would have changed about the
What's
picture.
this one, the first one is
What's our word for slant?
two?
Slope. There you go. You're right. Yeah. The slope of the first line is 2. That makes sense, doesn't it? Think what that means. What's a slope of 2 mean? The rise over the run is 2. So anytime I run 1, which is a width of delta, right? For every 1 I'm going to run my delta, the rise, which is the epsilon, is increasing by 2, right? So because the epsilon is increasing twice as fast as the delta is going to have to be multiplied by 1/2, isn't it? Everybody see that? So it comes from that slope. Okay? If that slope had been 10, what would the relationship have been? Delta would be 1/10 epsilon. Yeah. Okay. Okay. So let's use a graphing utility. Okay, so this is a great Desmos type question, right? And I really want you guys to get good at Desmos. Desmos is an amazing tool. So here's f of x, and we're approaching what value? 0. Okay, and the limit is clearly, if I approach 0, is 6. Okay, so let's write f of x. No surprises there. As we approach 0, the value is 6. If the epsilon is what? 2. Okay, so if epsilon is 2, how could I represent that on Desmos?
Y
So, I mean, how can I represent that? We kind of did it in the last example. A lot of times you want to represent the epsilon as being, I could do 2 horizontal lines that define the upper limit and the lower limit of epsilon, right?
Those are 2
Y equals 8 was.
Okay, good. So like y equals 8, y equals 8 would be a good one. And y equals 4 would be a good one. right? Does that make sense? Okay, I can even do something else. I just kind of get you used to Desmos a little bit here. I could even do something like this. I could even say something like y equals L plus delta. I'll call delta, or plus epsilon. I'll call epsilon E. Okay, oh, you know what? I can't probably use E, can I? I wonder if it'll take that as, yeah, I probably can't. So I'm gonna make it a capital E, okay? And y equals L minus E. Okay, in Desmos, when you do stuff like that, notice that it auto-generates these sliders. So I can pick values. Well, what is my limit? My limit I could even define as, my limit equals, I think it'll do this. This might break it. Let's see. Limit equals f of, limit of, does it do that? I'm not going to mess with it. We'll partner out that later. So we could just say L equals, was it 6? Yeah, 6. Okay. And epsilon equals 1, how about? No, we want 2, don't we?
Yeah.
So I can drag this out to 2. Okay, and let's make both of these purple. See what I'm saying? That's kind of cool. Then I can use these sliders, and I can change this any way I want to. And I can just manually type in the values too for my sliders. I don't have to drag it. Okay? So far so good?
Yeah.
Yeah.
Okay? So that defines our epsilon. Now we want to choose the delta, right? So how could what's going to determine the delta here?
Where is
Or F.
Okay, where what intersects?
the f of x
And the top one, right? Okay. So now watch what we do here. Then I can, if I click on one of these, look, I can see there's an intersection, right, at 1.414, and there's an intersection at negative 1.414. Okay. So then, what did I do wrong here? X squared plus 6, epsilon equals 2. What the heck?
It's easier.
Oh, that's right, it's C's the answer. Yeah, duh. Okay, that's right. Yeah, I didn't see a 1.1.
It's just-
Yeah, does that make sense?
out of order.
Okay, so, right, it's out of order. But, so what would delta be then? 1.414, right? Okay? And if I want to do part 2, I can just shrink this down to 1.5, and now it shrinks to 1.225. There it is.
Yeah.
Okay? Pretty cool, right? So, using these numerical and graphical tools, that's how you do calculus in the real world. All right, moving on. So what about this one? Here's another one I want to just focus on a little bit. Now this looks different. What's different about these limits than the limits we've been talking about for the last day and a half?
There's a break on this one.
Okay, yeah, the plus and the minus notation, right? So we've got limit from the left and a limit from the right. Okay. So the limit from the right as x approaches 2 is clearly 0, isn't it? Right. The limit from the left as x approaches 2 is 1. So which of the following is the correct maximum value of delta such that the absolute value of f of x minus 0 is less than 2? So what's epsilon? 2. Everybody agree that's epsilon?
Yes.
Okay, so our distance from 0 is 2 whenever, now this looks different. That looks different, and you tell me what? What's missing there?
No absolute value.
No absolute values. Okay, how come? Because we're going from a specific side. Okay. When I say that x minus 2 is greater than 0 and less than delta, that means that this difference has to be positive. So is x greater than 2 or less than 2? be greater than 2. Do you see how that implies that we're approaching from the left? We're taking x values, we're precluding any x values less than 2 because the difference has to be greater than 0, it has to be positive, right? So we know we're approaching from the right. Well, if we're approaching from the right only, then we can effectively ignore. We can effectively ignore all that stuff over there and just focus on the right. Okay? So now if we're just exclusively approaching from the right, and we want epsilon to be 2, well, if epsilon is 2, that's just going to be a horizontal line. The limit is 0, correct? So where's my horizontal line going to go? 2, and then the negative 2 we can ignore, because obviously the function's positive everywhere. Technically, we probably need 2 lines. So there's our line. So if that's the epsilon, what's our maximum delta? No, 2. Because this distance right here, there's the point of intersection. And that's delta, right? And that equals 2.
Yeah.
See what I'm saying?
Yeah.
Okay. All right. How would I specify we're approaching from the left? What would I have to change here?
Be a little plus, yeah.
It'd be the absolute value, or sorry, what would be greater than 0 and less than delta? If I want to specify values of x less than 2?
You would add,
How would I do that? Like, I could do something similar. I could write the same problem,
2 minus x.
2 minus x. Yeah, I could do something like, let's say we wanted f of x, the absolute value of f of x minus, but now it wouldn't be 0 anymore. Now it'd be 1, f of x minus 1 is, let's say, less than 2 again, arbitrarily, right? If we want that to be true, then we'd have to say, for our neighborhood, that 2 minus x is greater than 0 and less than delta. So now we're picking values of x that are slightly less than 2. So we're approaching 2 from the left. And what would the answer be there? So I'd have to take this thing, and scoot it up to there.
yeah.
That'd be 1, wouldn't it? In this case, the width of delta would just be 1. Make sense?
Yeah.
Okay. Okay, so then last part. So, so here's a part where, what am I doing here? Okay. So what if we want to find the value of delta required to do this? Okay, what's our epsilon?
0.0.
So 0.01 is our epsilon, correct? Okay, that's our target accuracy for how close we need to get to the actual limit. We define the function as 2x minus 5. We're approaching the value c. Okay, if we take that limit, what's the limit of 2x minus 5 as x approaches 3? 1. Okay, so that's L, right? That's the limit. We need to be within 1/100th of 1. Okay, and we want to figure out what does the delta need to be. Anybody want to take a guess? Or take a stab at it. It's probably not a guess. Epsilon is 0.01. Wait, want to stab at what delta need to be? Well, let's see.
Is it
Let's see.
0.005? Oh, yeah.
What? 0.005. That's correct. Well, let's see why. Let's see why. Okay, so how can we do this? Well, here's how we can do this algebraically. This is pretty cool. This is, and I want to, once again, you're not going to do a lot of this stuff. I mean, this is, I just want you to see mathematically how we accomplish proof-oriented answers like this. Okay, so we're going to start off with this expression. Okay, and the expression representing epsilon is related by the function to the expression representing delta, right? They're tied together by the fact that it's the same f of x. And when we calculate the limit, we're evaluating the limit at c. So this is going to seem pretty mysterious the first time I go through it, but really this, if you think about this a little bit, what's about to happen shouldn't be that surprising to you. It kind of has to work out this way. The math gods ensure it, right? Because this is a limit that exists, and those two, you know, the epsilon and delta are intrinsically related by the fact that we know what the function is and we know what value we're approaching. Here's how we get there. We're going to start with the expression of epsilon. So we have the absolute value of f of x, which is what?
Or 2x.
Minus L, which is what? 1, is less than epsilon, okay, which is 0.01, right? Let's just do some algebra on that. Now we have to be careful when we're doing algebra with absolute values, but as long as we're within the absolute values, we can do regular algebra. So what can I do inside? Combine like terms. So I get the absolute value of
2.
minus 6. Now what? This is good practice doing algebra with absolute values too. What else could I do inside?
Take it
I could factor a 2 out, couldn't I? I could write that as the absolute value of 2 times x minus 3. Okay, now, how about this one? What can I do there? If I've got, just in general, if I've got the absolute value of a times b, what must that be equal to? Has to be, doesn't it?
Yeah.
Right? If I'm looking at a product of factors, regardless of what the signs of those factors are, their product is going to be made positive. That's the very same thing as making each factor positive first. Doesn't matter. The magnitude stays the same, right? It's just that the sign's positive either way. So what's that imply here? So we're going to get the absolute value of 2, which is what? 2 times the absolute value of x minus 3 is less than 0.01. Well, that's just a 2. Okay, now this is starting to look suspiciously like a delta statement, isn't it? What does delta say, right? If you think about what delta is saying, let's go all the way back to it. Delta says the absolute value of x minus c is less than delta. That's our delta statement, right? Okay, well, what's c in this problem?
3.
Ah, c is 3. That's x minus c, right? So what's the only thing I have to do to isolate that absolute value?
Divide by 2.
Divide by 2. So look what I get. If I do that, I get the absolute value of x minus 3 is less than 0.01 divided by 2, is 0.05, right? So that's c, and that's delta.
Okay.
Make sense? Okay? Okay, so okay, how about this one? Let's go one step further. So now we're actually going to do a proof. And I just want you, I'm not going to expect you to do this, but I just want you to see this one time. So this is how we would formally prove this thing. If I want to show that that limit exists, if I want to show that this limit exists by using our epsilon delta definition, our formal definition of a limit, we could do the same thing we just did. First of all, we could say, okay, well, let's just assume that that there's some epsilon, some positive epsilon that exists that we could choose. We don't have to even specify, we'll just call it epsilon. Okay? Well then by starting off with the definition of epsilon, absolute value of f of x minus L is greater than epsilon. What does that become for our specific function? 3x minus 2 minus 4 is less than epsilon. I could combine like terms. Maybe we'll combine a few steps. I can combine like terms and get 3x minus 6. Is that the same one we just did exactly? No, it's a little different. Okay, good. Is less than epsilon. I could split that into the absolute value of 3 times the absolute value of x minus 2, and then the absolute value of 3 is just a 3. So we'll combine a couple steps here. So we get 3 times the absolute value of x minus 2 is less than epsilon. And so we end up then with, finally, our delta statement. Absolute value of x minus 2 is less than epsilon over 3. Okay? So that tells us that delta should equal epsilon over 3. We might call that our preliminary value of delta. So we figured out what should the delta be based on the behavior of the function. Okay? Now, we can go back to this original thing, and we just want to show that if I go through the process here of writing out our statement for delta, that we can come up with an epsilon that works. That we actually come up with a value, that there is some real, we're going to assume that we just assume epsilon, there's a positive epsilon that's going to work for this function. If we make that assumption and everything works, then that assumption is true. Okay? So let's work in parallel over here then. So if we start off with our delta expression, the absolute value of x minus delta yeah. I gotta think how this works. We did this after school yesterday. And this all works so nicely. I'm sure this is right. Where did I put that? Oh, I don't know. I'm sure this is right. So absolute value of x minus delta, delta would be an epsilon over 3, is I gotta think about this one. I'm generally using black hat. I think that's right. Tell you what, I'm not going to sit here and keep you captive. Once you guys, this is the last thing I wanted to show you, for sure. Oh, there it is. I did it on here yesterday. Yeah, yeah. There we go.
We've gotten to that.
Oh, we did that. We did that. No, I'm going to... I don't really want to do that one. That one's not work. That one's too good. Really do that one. I'm gonna pause this. You guys can work a little bit, and I'll pull you back the last 5 minutes, and I'll fix this.
Last one.
Okay. All right, last little bit. Let's wrap this up so we can be done with this stuff. Here's what I would do then. I would just say Okay, I'm going to start off with the epsilon expression. So I'm going to say the absolute value of f of x, which is 3x minus 2, minus 4, has to be, what's that equal to, first of all? That has to be less than epsilon, correct?
Yes.
Okay. So this is equal to, if I do the algebra in here, we've already kind of done this stuff. We get a 3x minus 6. We just get 3 times that times x minus 2, right?
Yeah.
Okay. Which is equal to, what is x minus 2? Well, x minus 2, that's x minus c, correct?
Yes.
So we know that the absolute value, if we write this as 3 times the absolute value of x minus 2, we know already that that has to be less than delta, which is epsilon over 3. Agreed? So we know that this whole thing has to be less than, right, what we started with up here has to be less than 3 times delta. And what's delta? Delta is epsilon over 3. Agreed?
Yeah.
So then we end up with what we started with, right, which is just the absolute value of f of x has to be less than, it's equal to this, but this has to be less than 3 times delta. Well, what's 3 times delta? Epsilon, right? So we just proved it, right? So we just showed that the absolute value of f of x minus L is less than epsilon if we make that substitution. And so it works, right? By just choosing this reasonable value for delta based on the behavior of the function, we showed that, yeah, this has to be true. The function has to be within epsilon of L, okay? So that's how we would formally prove this. Now we tied up all the loose ends and we can absolutely, there's no wiggle room on this. A limit, which we already knew, right? We already knew a limit works here based on our discussions of the last 3 or 4 weeks, right? But now we tied it up with an epsilon delta proof, okay? Just wanted you to see that. It's not like that's something, like I say, you're going to be doing a lot of,
Yeah.
but you will see it again, next year in college. You're likely to, probably you'll see that again.
Quite a few layers.
You may not, but if you're a math major, you will for sure.